So, welcome to my fourth lecture. So, indeed, tomorrow everything in this conference will be over, and I'm also a bit sad, like Ali, because it has been really great so far. So, as there are 2 classes left, I'm going to go a bit more into difficult stuff and to go closer to my current research. So, today I will first give you quickly the idea of a bijection of Schur's theorem, in which you will see that some parts congruent to 1 modulo 2 and some parts congruent to, 1 modulo 3, and some parts congruent to 2 modulo 3 will come together, which was hinted at with our refinement yesterday. And then I will talk to you about the method of weighted words, and we'll see how far I go. So, well, maybe it's now the 3rd time that I will write Schur's theorem on the blackboard, but I will write the refinement that we found yesterday. So, okay, so Schur, so Schur's theorem refined. So we could say that this is due to Al-Abdi and Gordon. So some slightly less precise refinement was due to Andrews before that. And that was in 1993. So this is what I told you yesterday. So for all n, uv, the number of partitions of n into u distinct parts congruent to 1 mod 3 and v distinct parts congruent to 2 mod 3 equals the number of partitions of n into u parts congruent to 0 or 1 mod 3 and v parts congruent to 0 or 2 mod 3, satisfying the difference conditions that we saw. So, I can just write them again, it's not a problem. Okay, so, and obviously the partition was written from that one, etc. Okay, so this is what we saw at the end of yesterday, where we added those 2 additional variables u and v. And so here, if we look at u and v, here you see, okay, so u, it's just the parts congruent to 1 modulo 3. Here is just the parts congruent to 2 modulo 3. But here, if you have some parts congruent to 0 modulo 3, they will be counted both in u and in v, okay? So this is what can give you the idea when you try to do a bijection to actually put together some parts here colored, congruent to 1 modulo 3 and some parts congruent to 2 modulo 3 together. That would contribute both a u and a v, and that would form a part congruent to 0 modulo 3. Okay, so that was the idea behind the bijection that was done by Bressou in 80, I think, 1980. Okay. So, of course, you could say that's strange because I wrote 93 here and 80 there, but if you listened and not only read, I said that Andrews had a bit less precise refinement before that, where instead of having U and V, he had just one letter, let's say U, U in both cases, and here also. And actually, even from just one letter in the refinement, you could already get that idea. So this is, this is why. So yeah, I can add it here maybe Andrews, but yeah, I forgot the year, the exact year. Okay, so actually, even though I don't know actually how Bresu found this proof, he must have read probably Andrews' paper. Yes?
Sorry, I feel like you just said this, but how are we distinguishing the U and V in the second case when they can both be 0, 1, 3?
How I can what?
Distinguishing the U and what U and V count in the second case, because they can both be 0, 1, 3?
So it's not really, I don't know if it's really about distinguishing them. It's just, yeah, let's assume you get some part congruent to 1 mod 3, then this part will add 1 to your number U. If you have a part congruent to 2 modulo 3, it adds 1 to V. And if you add a part congruent to 0 mod 3, you add 1 to U and to V.
I see.
Yeah. Okay. Maybe it will be even a bit clearer later when I do some generating functions with the weighted words, but okay. So far, we can just see it like that. Okay, so I promised I would merge some parts together, so we'll do that in this bijection. So I'm warning you, I'm only going to do one direction of the bijection in detail, and I will give you a reference for the other direction, because I want to talk about other things too. But I just want to show you that there will be some merging of parts, and you will see that, so I will be happy. Okay, so we start with partition pi into distinct parts congruent to 1 or 2 modulo 3. So a partition of this type. And we will try to transform it into a partition of this type, satisfying the difference conditions. Okay, so you read the parts of pi into a column. So far, nothing too fancy, so let's do some examples, because bijections are always better on examples. So I must admit that I stole this example in the book of Andrews and Erickson called Integer Partitions. And actually, that will be the reference for the full bijection that I will give you. So maybe I can already write it here. So Andrews, Erickson, integer partitions. It's a nice book, nice introduction to integer partitions. Oops. So, okay. So you start like that, and you read the partition from bottom to top, like that. And along the way, if you see some pair of parts that does not satisfy these conditions, then you merge them together into a part of bigger size. Okay, so let's do like that. So if there is a pair of parts which does not satisfy our relation star, I always call it star, I continue, merge them. Okay, so let's do it here. So we look at the first one, 1 and 2. That's already not okay, so we merge them. So we write 2 plus 1. Then we continue, so 5 is okay, 8 is not, well, between 5 and 8 it's okay, but between 8 and 10 it's also not okay because you have difference only 2. So okay, you put them together as well. So we write 10 plus 8. And well, here there would have been a problem, but we have already merged that, so yeah, we can just write 11. Okay. So in this partition we obtain, we have that the new parts that were created are multiples of 3. And that's actually what I wanted to show you, because the problems only come when you have two consecutive parts that are congruent to 1 and 2 modulo 3. In any case, we don't have any part congruent to 0 modulo 3. And if you take two consecutive parts congruent to the same thing modulo 3, they differ by 3. So we are OK. So the only problems come if you have either 3k minus 1 and 3k plus 1, or 3k plus 1 and 3k plus 2. OK, so here, the new things that were created are multiples of 3. OK, so let's write this here. The new parts that were created are multiples of 3. And also, very importantly, and no consecutive multiples of 3 appear, because we want the two lines of our equation star to be satisfied. So we will see why. 3 appear. OK. So, because, for example, the worst possible case that we could have would be if you had in pi something of the shape 3k plus 1, 3k minus 1, 3k minus 2, and 3k minus 4. Like you have a lot of consecutive terms that do not satisfy what we want. So the worst case. So here we would merge those two together. We get 6k minus 6. And we merge those two together, we get 6k. So that's, you have a difference 6 exactly as we want. And there is another possible worst case where you start with something congruent to, wait, that was 2 modulo 3, so it's something congruent to 1 modulo 3. So you could have also 3k minus 2 followed by 3k minus 1, then 3k plus 1, then 3k plus 2. And here again, if we add these two, it gives 6k minus 3. And those give 6k plus 3. So again, we have a different 6. OK, so when we do that, we actually, at least between the parts congruent to 0 modulo 3, we have the difference conditions that we want. And yeah, among the other, if you remove those parts also, they have those nice conditions. OK, but we are not over because, of course, like it's not even in the right order, and we should still check that everything goes well together. But actually, here we will do a trick that I first mentioned when I talked about the Rogers-Ramanujan identity. You remember I told you that if you consider partitions with difference 2 between two consecutive parts, you can create such a partition in a unique way by taking a staircase of step 2, so the partition 1 plus 3 plus 5 plus 7, etc., which has difference exactly 2, and adding to it a partition with the same length, with no particular additional condition, and the result would have difference at least 2. So following a bit maybe the same inspiration, Bressou had an idea here. It is to actually remove from this partition a staircase with step 3 this time. Because here we mostly want difference 3 between two consecutive parts. So, OK, so that's what he did. So I'll continue like that. So remove a staircase of step 3. So that would be like 0 plus 3 plus 6 plus 9, etc., etc. OK, so let's do this. So here we would have, so we remove 0 from the lowest part. So we get still, well, now I write 3 instead of 2 plus 1. Why not? We remove 3 from 5. We get 2. We remove 6 from 18, and that gives us 12. And we remove 9 from 11, which gives us 2. And we still write next to it the parts of this staircase that we just removed. So like we split our partition into two two subpartitions if you want. Okay, and now you rearrange this first column in non-increasing order. So here that would give us 2, 2, 3, 12. And still next to it, you keep the staircase untouched. Okay? So now at least what we have here is also a partition, because here it was more like a composition. It was not in the nice order. And once we have done that, we add the staircase again. Okay, so what do we have here? We still have 2, then 5, then 9, and then 21, unless I'm mistaken. And indeed, here you have a partition that satisfies the difference conditions before. So satisfies the difference conditions star. So why is this true? So first of all, as I said before, if you take whatever partition and you add a free staircase, actually, yeah, when I write free staircase, it's the same as staircase of step 3. I use different words, I'm sorry for that. So if you have the free staircase, then definitely you will always have a partition with difference at least 3 between two consecutive parts. So this is almost star already. And actually, I just said there that, so at this step, that among the multiples of 3 that we have created, that there were no consecutive ones. So actually, that's still true after you do all these manipulations. Like when you put your staircase again, you would also not have any consecutive multiples of 3. So this is the two conditions of star, and we are done for this direction. Actually, the reverse bijection is a bit harder. So, I mean, either you can read, if you're interested, the paper of Dousse, or you can read this chapter in the book of Andrews and Erickson. And actually, in Andrews Erickson, they write it a bit more as an exercise, but with several steps that I think you can follow. So, I think, yeah, I personally prefer slightly that presentation of things, but that's up to you. So, okay, so here we saw one of the interests of having a refinement, which is that it can give you ideas for doing a bijection. Okay, so any questions so far? All good? Okay, perfect. So now I will move on to actually the method of weighted words that I have promised for quite some time. I'm just checking where I am according to time, so that's perfect. I have around half an hour left, which is perfect for introducing the method of weighted words. Okay, so I will still give you the example of this method on the same theorem. Now that we are used to it, I'm adding the new difficulties like sequentially. So we have already refined it, but we will see that there is even a version that is even more refined than that, if you want, or maybe more like a generalization, if you want, and which was given through the method of weighted words. Actually, I will put that up also. It will be already done for later. Okay, perfect. So let me explain to you what it is. Okay, so I will write that. So method of weighted words. Yeah, actually, I have maybe a bit of problem with the use of the word method, because I would rather use approach, maybe, because as you will see, there are some steps of the so-called method that can very widely vary. So I'm not sure if you can call it a method in that sense, but definitely the first steps are a method. And so I think, in any case, it's known under that name. But don't expect an algorithm that will solve everything from the beginning. That's all what I mean. So this is also like from Aladi and Gordon. And actually, when they proved that, they proved actually the stronger statement that I will soon explain. So it's still in 1993. Okay, so far we had been studying partitions into positive integers. So we were considering simply the numbers 1, 2, 3, 4, 5, etc., etc. Normal. But, for example, for Schur's theorem, what they had seen and proved was that actually you can refine it according to the values of the parts modulo 3. And that makes sense because the conditions, they depend on values modulo 3 on both sides, so that's sensible. So actually, the original idea of the method, and that's a step that is always the same in every different version of the method, is that instead of considering just the classical integers as we did here, we actually want to consider some colored integers into here 3 colors. But let's imagine all the conditions would be, I don't know, modulo 7, we would consider partitions into 7 colors. So we take a reasonable number of colors depending on the conditions. So okay, so we'll do that. So we want, instead of considering those integers, to consider something like 1a, which would be less than 1b. We also need or at least it's very useful to have an order like that. Maybe it's not strictly needed depending on the version of the method, but okay, let's do it like that. Let's put the order already. Okay, so here you see we will have 3 times the integer 1, for example, and that's true for all the positive integers. But you have a version where it's colored A, a version where it's colored B, and a version where it's colored C. And actually you want a transformation from those colored integers to the usual integers. So we're going to do it so that it corresponds like vertically. Let's be simple. So okay, so actually we can do like the most easy transformation that we can think of, maybe, because everything is modulo 3. We can say if you have some integer k colored A, the correspondence, maybe I can do it like that instead, would be like 3k minus 2, because the integers colored A, we want them to correspond to 1 modulo 3, okay? So we do like that. Then an integer kb. So if you look at this example, what do you want it to correspond to? Does someone want to give it a try? Yes?
3k minus 1.
Thank you, great. Good answer, 3k minus 1, indeed. And, oh, I did something wrong, I'm so sorry. Actually, that was a 2. It's just for we could make it work that way, but it would be a bit not always super nice, so for convenience. So if we want 2c to correspond to 3, then that means we would like to transform kc into 3k minus 3, okay? Okay, so those are the correspondences between colored integers and normal integers. Okay, so if we consider, so the partitions that will use those parts, I will call them colored partitions, or sometimes also non-dilated partitions, because I say that these 3 transformations are dilations, if you want, because you increase the size. So yeah, maybe I still need that. So okay, let's say we say that those are dilations. Okay. Okay. So and actually, if we want to think in terms of generating functions, so in terms of generating functions, if the power, if you take a generating function with several variables, in which the power of q counts the number that is partitioned, or like the weight, but maybe we'll use the term weight. That's simpler because we've seen it in other lectures. Okay, so if the power of Q counts the weight of the partition, and the power of A counts the number of parts colored A, we can also, we just take the same variable as the color because it's simpler in the generating function. So number of parts colored A, and we can also, like, we do the same for B and for C. Then the dilations correspond to doing so replacing Q by Q3, because here everything is multiplied by 3, and replacing A by AQ minus 2, B by BQ minus 1, and C by ABQ. Sorry, that will become later. C by CQ minus 3. Okay. Okay. And also one thing that is always the case in this method is that here we have some difference conditions, but so far they are on those integers, like the classical ones. But we want to translate them in an equivalent way to the colored integers. Still checking the time. Okay, very good. So let's do that. So actually, here we wrote it more like a sentence, but I like to write it as a matrix or a table, because I'm actually not doing any algebra on the matrix. It's more like a table if you want. So we'll do that. So maybe I split this into two. So okay, so dilated difference conditions and non-dilated. Okay, so maybe here also I read. So this is dilated, and this is non-dilated, because I don't want to get you to get confused between those two things. Okay, so the dilated difference conditions is actually just what we saw here. So it's just star, but if I rewrite star as a matrix, we could write it like that. So A, B, C, A, B, C. Okay, so actually here A means 1 mod 3, B means 2 mod 3, and C means 0 mod 3. Okay, so if you have a part congruent to 1 modulo 3 followed by another part congruent to 1 modulo 3, you can have difference 3, right? It's in my difference condition star. Okay, why not? Then, if you have a part congruent to 1 modulo 3, followed by a part congruent to 2 modulo 3, then, of course, in theory, you could say that you have difference at least 3, but in practice, you will never have a difference 3 between something congruent to 1 modulo 3 and something congruent to 2 modulo 3. So actually, if we write the exact minimal difference, here that would be a 5 instead. And in the same way, if you have a part congruent to 1 modulo 3 followed by a part congruent to 0 modulo 3.
Would it be 4?
Is it 4?
Okay, I always confuse. Is
the
rows?
Here it's lambda I, sorry, and here is lambda I plus 1. So if I have something.
I'm doing things in reverse order.
Oh yeah, sorry, but it's good that you asked the question actually. Yeah, I'm so used to doing it like this that I sometimes forget to be precise. So yeah, so this, in the rows, they correspond to the first part of the partition, so lambda I, and here in the columns you have the following part, so lambda I plus 1. Okay, so in the same way, if you have something congruent to 1 modulo 3 followed by something congruent to 0 modulo 3, okay, in theory you could have a difference 3, but that never happens. But what can happen is difference 4. Okay, so I think you understood the principle. I just filled the rest of the matrix myself. And so On the diagonal, actually, you probably recognize a bit more what looks like star, because it's always things that have the same congruence class modulo 3, so that makes sense. And so this is, let's say, this is the matrix of dilated difference conditions. And we want to find some correspondence between also a matrix of difference conditions, but this time on those non-dilated integers that would correspond with these dilations to this matrix. Okay, so I'm using the same symbol just to show that it's the same correspondence. So we will try to write this. So we still have A, B, C, A, B, C, and it's still, well, it works in the same way. If I look at the coefficient AB here, it's the minimal difference between a part of color A followed by a part of color B. Okay, so let's look at this. So there is some automatic way to go from here to there and from there to here. I don't think it's fully detailed in general in the several papers that do the weighted words method, but maybe I will give some small details here. So, okay, so let's say we have some part, lambda, L, not lambda, L, and I read dil in subscript to just show that it's one of the dilated parts, to not have any confusion. So let's assume it's congruent to M modulo 3, and with M being 1, 0, 1, or 2. And here I wrote the correspondence between non-dilated part and dilated part by doing the transformation in this direction. But actually, this one we can also say that it will correspond to some part, some non-dilated part, which would be equal to your dilated part plus 3 minus m divided by 3. So that's a kind of general formula. And so yeah, this is how I define L non-dilated. And we'll consider some other part, L prime, which is also dilated, and which would be congruent to M prime modulo 3 again. And this would correspond also to lambda prime with obviously the same formula, except now you have M prime instead of M. Okay, so you have things like that. So now let's assume that L and L prime are two consecutive parts of the partition. So if L and L prime are, let's say, yeah, consecutive parts, such that you have lambda, yeah, actually lambda prime is the biggest here. So that lambda prime is equal to lambda plus some difference condition, also dilated here. Then, after we do our transformation, actually this one, we would obtain so if we go to the non-dilated level, we obtain the following. So we just take this equation and we try to make those numbers appear, because actually what we want to know in the end is some expression of the same shape with lambda prime non-dilated. I don't know why I always say lambda. L prime non-dilated, L non-dilated plus some non-dilated difference condition. Okay, so that's what we try to do. So we want to make these formulas appear. So we just take this equation and we add what we want here on the left to get actually this. So we just write lambda of L prime. I think I will say lambda forever, it's okay. So L prime dilated plus 3 minus m prime, and we divide by 3. And so on the right, we have to do the same thing. So we write L dilated plus the difference condition, dilated plus 3 minus m prime. We divide by 3. Of course, that's still true. And actually here, this is almost what we want here, except we have minus m prime and not minus m. But we can very well do plus m prime. Now what am I doing? No, minus, sorry. Minus m plus m. That's all good. So actually, if I take this, this and this, that's what we want here. Okay? So this is actually the non-dilated L plus the dilated difference plus m minus m prime. But I will write this minus m prime minus m because I prefer it that way, over 3. And so that was L prime non-dilated, okay? So this would be actually what we obtain here is the non-dilated difference condition. Okay, so actually to construct this matrix, we can just consider all those minimal allowed differences, and you use the formula that I just derived to fill all the entries. Indeed, I still have to maybe justify that this is divisible by 3, indeed. But the difference here is equal to L prime dilated minus L dilated. So modulo m, that would be equal to m prime minus m. So that should be all fine. Maybe I also write that in red. So this thing is congruent to m prime minus, that's not a prime, m prime minus m, but 3. And we remove m prime minus m, so it's all good, divisible by 3. Okay, so I hope you're convinced. We are not doing anything crazy. Okay, so let's just look. So actually on the diagonal, it's actually very simple. You don't even need to do all of this because you have m equals m prime everywhere. So you just divide the difference conditions that you had here by 3. So that's quite quick. So that we would get 1, 1, 2. And as an example, I will do this one. So we had here 5 as a non-dilated, as a dilated difference condition. So that would be 5. And then the bigger number, so L prime is A. So that's congruent to 1 modulo 3. And L would be 2 modulo 3. So here we would have to do 5 minus, between parentheses, 1 minus 2. So, and divided by 3, obviously. So, okay, maybe I can just, I like the orange today, so let's do it here. So we want to do 5 minus 1 minus 2 over 3. So that would give actually 6 divided by 3, and so that would be 2. Okay, so here we put a 2, and we do that for all the entries, but obviously I won't lose time by giving details for all of them. Is the method clear for everyone? How to go from one to the other? Okay, very good. So thankfully I computed that beforehand, so I can just copy my notes, and here it is. So this is a non-dilated matrix, which corresponds to Schur's theorem. Okay, I will check the time one last time. Okay, very good. Okay, so this is what is common to all the different versions of the method of weighted words. So far, it's like fully a systematic method. You start with some identity, which has some congruence conditions and some difference conditions. You try to translate it to the level of non-dilated integers. So you have a systematic way to do that. And now comes the part that varies depending on the method. You want to prove a non-dilated partition identity by considering the generating function for partitions satisfying those difference conditions. And you want to show that the generating function is an infinite product because you also want to have congruence conditions, like in Schur's theorem. So I will do that. And I will tell you a bit about two different approaches for that. So the original approach is, of course, by Aladi and Gordon, and there is another approach by myself. And yeah, they are quite different, but they... Oh, that's nice. Okay, so let's say, Aladi-Gordon approach. And my approach. Okay, so in both cases, our goal is to compute the generating function for those partitions. Okay, so maybe, yeah, goal, that's true for both. Compute the generating function. Did I give it a name? Not really. So for the non-dilated partitions, which satisfy the difference conditions and show that it is an infinite product. Okay, so yeah, and my goal is the same. But so first of all, we need to find maybe some restrictions on the colors, because ideally we would want a generating function that has 3 color variables A, B, C, and that we are able to keep track of the number of colors A, B, and C. That's in an ideal world, but things in mathematics often don't work fully ideally. So actually, very often you're not able to keep track of all the colors. For example, on the left top blackboard, what I wrote for Schur's theorem, there were only 2 colors, A and B, if you want. So something must have happened to that poor variable C. And so actually, in the approach of Aladi-Gordon, they didn't put that much detail on that step, so I don't know exactly how they deduced what happened to the variable C. But I can explain to you how I do it. So to find, we want to find some possible restrictions on A, B, C. So what I do is I just look at the very first terms of the generating function for partitions with difference conditions. So here we would have, of course, always the empty partition is okay. We can have one part colored A or one part colored B. You don't have one C in the order initially, so I don't have anything with one C. Then you can have AQ squared, BQ squared, CQ squared, and some other things. But actually, even if we stop here, I think this will be enough to find the conditions, because we want our generating function to be an infinite product. That's super important. So maybe I even should emphasize this a bit more. And so if we look at the first terms, and we want this to be an infinite product, then there are not that many choices. So if we want that, that means that in our infinite product, there is something that will start with 1 plus AQ. Otherwise, we wouldn't have that, right? So, okay. Then either, we don't know if it will come from something of the shape, let's say, minus xq something infinity, or something of the shape xq something q something infinity. But we want, we want only factors of both those, of one of those shapes, or both of those shapes. Okay, so the first term of either this or this should start with that. And if it's something of this shape, here I would close my parenthesis. And if it's something of this shape, I would still have plus a squared q squared, etc., etc. But I don't know so far. Yeah, let's put some dashed parentheses. I don't know if it continues or doesn't continue. But in any case, the BQ, that's another term with Q. So whether we are in that case or that case, you wouldn't get just another term with just Q. So we know that this should come from another factor. So okay. So we start by writing some other product, 1 plus BQ. And again, I do a dash parenthesis because it could be that if it's of that shape, it continues, or if it's of that shape, it stops there. So we have this. But of course, if we have this, we have the term 1, the term AQ, the term BQ, but we also have a term that corresponds to the product of both, right? So actually, we must have a term ABQ squared. So we must have a term ABQ squared. And so here I wrote everything up to q squared. The next terms would be at least q3. So the terms in q squared, you have aq squared, bq squared, and cq squared. And actually, aq squared and bq squared, well, they are more likely coming from the same infinite product than those. So like, they would come. So here it's a bit heuristic. You can make it a tiny bit more precise, but you would already have some factors like that, let's say. So it makes sense that here the cq squared, if you want to obtain some abq squared, well, actually we cannot keep the c, and we should set c equal to ab, because otherwise we couldn't have this term. So we set c equal to ab. So we have a first condition here, and you can keep doing that for a little while, and actually you see that if you follow this strategy, for a while you don't have any other constraints that come out. So then, I don't know, you take a computer or something, and you try to, you conjecture that if you set a equals to ab, this would be, the generating function would be equal to the infinite product minus a q infinity times minus b q infinity. And you see that no matter how far you go with your computer, it seems to be true. So here you think, okay, I have found the correct conjecture for the formula that we want. And so you can try proving that. I'm not sure, but I think at least in some of their papers, Aladi and Gordon, they tend to keep all the variables a bit longer and try to compute generating functions using Q-series, and then they see that they cannot get a product if you don't have some constraint, and they introduce them there. But I don't know if it's the case in all their papers, but personally I prefer doing it at the start, and then we have like all the conditions that we wanted. And I'll just finish by making my table a bit longer, but oops, sorry. And I will explain the last difference between our two approaches. So here I don't know exactly how they did it. Maybe they even do the same, but they just didn't write it in the paper. It's possible. So here, what they do here is that they use the idea that just like for Rogers Ramanujan, you know, when you decomposed as a staircase with difference exactly 2 and a classical partition, they use the idea that the generating function for partitions with difference at least something between consecutive parts consecutive parts equals the generating function for partitions with difference exactly something times 1 over QQ, let's say M, I don't know, where M is the length of the partition. So that was really the same idea of what I told you with Rogers Ramanujan. So they use this idea in more generality, and so they do all this with the colors. So actually, if you have some color sequence, you can relatively easily, by looking at the matrix, find the minimal partition. So let's just do a very quick example for that. So if you want the color sequence to be C, A, B, B, C, then, so this is the smallest one, let's say. So the smallest value for C was 2, okay, in the order there. So the smallest part would be 2C. And then you would have to look at the matrix. So between C and B, because if we go in the reverse order, we now look at first the column and then the row, you have difference at least 1. So that would be 2 plus 1. So that is 3B. Then you want another B, and you have difference 1 between B and B. So let's put 4B. Then between B and A, you have 2. So that would be 6A. And then you have between A and C, you have 2 again. So that would be 8C. Okay. So for example, the generating function for all the partitions satisfying those difference conditions and with this exact color sequence would be, well, I haven't computed actually this generating function, but yeah, you could do it. The generating function for this partition divided by QQ sub 1, 2, 3, 4, 5, 5. Okay. So, and more generally, they do that for all the possible color sequences, and they use always this argument, and then they sum over all the possibilities, and they find, in the end, some Q-series expression. So, for example, here they show that the generating function is equal to the sum of Rs, A to the R, B to the S, Q to the R plus 1 over 2 plus S, S plus 1 over 2 divided by Q, Q sub R, Q, Q sub S. And yeah, they show that it is the infinite product that I have conjectured there. So minus AQ, Q, infinity, minus BQ, Q, infinity. So that's their approach. And actually mine will go quite fast because it's more or less what I showed you yesterday. So I define, so it's very different. For me, I never compute a representation like a sum like that. So I just define some generating functions, GKA, GKB, GKC, the generating functions for partitions. So yeah, of course, this is always non-dilated and also for them, obviously. Partitions satisfying the difference conditions. such that the largest part is at most Ka, Kb, and Kc, respectively. And then I use the matrix to find recurrences for those generating functions, exactly like we did yesterday, but without, no, actually the day before yesterday, we did the equations. But it wasn't with the matrix, it was just with the same difference conditions, but more in the form of a sentence, but it's the same idea. So actually, those recurrences are really easy to deduce when you look at the matrix. You can just check, okay, if my first part is Ka, you look at this, like if the second part is also of color A, it's 1 less. If it's of color B, it's 2 less. If it's of color C, it's 3 less. So it's very automatic. So yeah, this is automatic. And it was implemented by Ali and Jakob Ablinger in a very nice Mathematica package, which, yeah, I think is very useful to prove these kinds of identities. And yeah, then of course you need to solve the equations to find the limit when K goes to infinity of one of those, doesn't matter which one. Let's say K, I don't know, like I will write C prime where C prime is whatever color is the simplest to compute. So, yeah, so actually there are some cases where this method is a bit hard to apply and in which one, like this one was easier. Like for example, Sziladich theorem, which is an identity with a very, very big matrix, like with 8 by 8, and so then if you want to analyze really all the possibilities for the color sequence, it can get tricky, whereas at least this remains automatic. So in many cases, this one works. But this one also, like even recently with my colleague Isaac Conan, we had actually to use something a bit more similar to that one. So there are some situations in which this one is better as well. So it's good to have two approaches, and depending on your problem, you pick whichever one works better. So I will stop here, and tomorrow I will tell you what I do in my own research with those weighted words. Thank you very much.